can put on the pocket. Yeah.
Is it on?
Yeah, it's on.
Perfect, thank you. It's very nice. Okay.
Are we on time?
Yeah, it's 10, I think.
Should we wait 2 minutes?
I don't mind. I can write down the title. I decided to change the title a little bit, so I was going to, well, I will still going to talk about string scattering amplitudes on ADS following on my talk on Friday, but in a more informal setting. And basically, I wanted to remind you the structure of those amplitudes, and then I will describe some patterns that we have found for those amplitudes. And in particular, I will describe some monodromy relations on ADS that we have found for open strings. Yeah, we can wait. Yeah. Okay. So yeah. So thank you very much for this. I am enjoying this workshop very much. So we have seen on Friday, and I will remind you, that string scattering amplitudes in ADS can be computed in a small curvature expansion. Can you see if I write here? Yeah. Can be computed in a small curvature expansion where the first term is the flat space amplitude, the second is the first curvature correction, and so on. And we have seen that for closed string amplitudes, so the structure for closed string amplitudes is that the amplitude in flat space, as we know very well, admits a worldsheet representation, which is an integral over the complex plane. Here I am absorbing alpha prime into the definition of S and T. So we have this integral representation that you can find in Green, Schwarz, and Witten. And then ADS corrections, further ADS corrections, the proposal is that these corrections are given by taking the same integral representation and in this integral representation, you insert certain beast, and this beast, let me call it generically W3K, which is a function of S, T, and Z. And to be a bit more precise, of course, this could be an empty statement if I don't tell you what the dependent and, sorry, my font is very large, one of these single-valued multiple polylogarithm of weight 3K in the variable set. Okay?
So can you just remind me,
Yes.
I know you did it in your talk, but just
Yes.
remind what the relation of ADS-ST is with the usual correlation function.
Right, right. So yes, so basically there is a chain of transformations. So first, you take the correlation function which is a function of the two cross ratios, u and b, and then from this you go to Mellin space. You go to Mellin, and in Mellin space you define what is called the Mellin amplitude of S and T. Shall I remind you that formula?
The formula doesn't have any ansatz, it's just a definition of
It's just a definition.
So it doesn't involve anything that you need to assume.
No. Okay. No. I mean, it is a formula. It is just like it's a Mellin transform. It's just a Mellin transform. And what is kind of what one would have to say, so the reason why this formula is useful is because, sorry, all nice properties of this correlator, like conformal partial wave decomposition, etc., translate into nice properties for this matrix M of S and T. And people has made conjectures for whether this exists for any conformal field theory, and that was proven in a paper by Shiboedo, Silva, and Penedones, that you can define these transforms non-perturbatively, that all the integrals converge, and these sort of things.
So you just need four-dimensional conformal theory? What do you need in order for this thing to be?
I am using it for n equals 4 super N Mills.
Yeah, so for n equals 4 super Yang Mills, that's a special case when you have n equals 4 super conformal. You need that in order for this ansatz to be?
You don't need anything. This is even for a standard conformal field theory without any supersymmetry.
Okay, but you say, okay.
Now, I use it for n equals 4 super N Mills because this is the amplitude that I am going to compute. But the Mellin, this, which is a bit outside the scope of. Sorry. Okay. If you want me to be 100% precise, let me be super precise. Good. So, in n equals 4 super N Mills, you consider the 4-point correlator of operators in the 20 prime.
Yeah, that's fine.
Right?
Yeah, the prefactor I'm happy with. Right?
Beautiful. And then you have a prefactor, which is this prefactor times some GUV. And then you can do the Mellin transform either at the level of the full correlator or at the level of the reduced correlator.
Okay.
I am only talking about the reduced correlator. So all the things I say are for the reduced correlator. Beautiful. Yeah, is that okay?
Is there also an integral transform from the Mellin to this?
Yes.
Yeah,
So, yeah, absolutely. So then, right. So then first from GUV, you do the Mellin transform, which gives you what people usually calls M of ST. And then there is another transform, which is a bit technical, but is simply the usual Borel transform. And this defines what I am calling A of S and T. Now, all these transformations are one-to-one transformations. So if you give me any of these three, I can compute in the regime where I am interested. I can give you all the three of them. So for convenience, I focus on this one because this is the object that has all these properties that I am discussing.
So the non-perturbed Mellin, I guess, is not necessary for a purpose, but is that something canonical?
Right, non-perturbatively, it would be beautiful to understand that. I don't know.
So you say there's a definition that was written down that's unambiguous, but maybe there's some choice.
So this Borel, absolutely. So there is, when one does this Borel transform, the only claim is that, and it was a claim done by Penedones, Giddens, etc., is that in this limit, in this flat space limit, as you take the radius to infinity, you recover the flat space amplitude, right? What I am doing is I am using this as my their formula, but for all R, as my working definition for what I mean by the amplitude. And that's what I am doing.
Yeah, I was just talking about the object in the middle, I mean the Mellin amplitude itself.
And the Mellin amplitude itself, this is supposed to exist also non-perturbatively and have some properties. And
Yeah, I guess I was just asking whether that number definition is something that's canonical or there's some choice involved.
I don't think, I think it's pretty canonical. I would say. Yeah. Yes.
So for the mailing amplitude itself, I thought the story was that it was better defined for large n queries because you could pull out double trace calls.
Yeah.
Is it the statement you said was that it's also well defined for any
That's right.
non-large n CSV?
That's right. Or at least that is the claim that Chiboedov, Penedones, and Silva do in their paper. That's correct. Yes. But here I am using it only for large n, because I am only using it to compute tree-level amplitudes. So I am using this in a very particular regime. I am using it for large n, and in a 1 over lambda expansion in n equals 4 super animals. So this is the safest place to use these definitions. And in this regime, it works 100%. Now, it could be that non-perturbatively in 1 over lambda, which is non-perturbatively in R, there will be non-perturbative effects, and this would be beautiful to be able to compute. I don't think they will have this structure, but that I don't have anything to say.
But suppose you had a world sheet theory.
Yes.
It would not be just the usual string on ADS, because that would compute G of U of V. Somehow you need to compute A of S of T.
That's why I wanted to ask you on Monday, why I ask you, yes, you're completely correct, because in the flat space limit, what you are recovering is an amplitude in momentum space, while here you have something in position space. On the other hand, all these things are one-to-one. So if you want, I can also give you the corresponding expansion for GUV.
Suppose I know how to compute the string on ADS. How would I ever compute A of S of T?
Well, can you give me GUV?
Yes, suppose I give you GUV.
Great. Then I do these two transforms.
Then you're not going to get that formula.
You should.
Oh, you say it's still the integral over d squared z is somehow going to translate from one to the other when you do this math?
My claim is that, and actually for,
Each value of z, you can get this math?
sorry,
Sorry?
It's a linear transformation. That's the phrase.
yeah, all these transformations are all linear. And my proposal is that this, as a function of S and T, can be written in the following this. Now, what I don't know is whether what I am calling C is what you will be calling C.
Yeah, that's what I'm asking.
That I don't know, because I don't know what you call C.
No, the location of the vertex operations.
No, but I think it was the same.
Each point on the world sheet.
Just like, you know, in ADS3, you can go looking different
Mhm.
bases.
So suppose we did this calculation in ADS3,
Yes,
right, where there is a worldsheet answer and there
Yes.
is an answer for GUV.
yes.
You would be, you guys have computed what A of S and T is in that context too.
Yes, this would be another talk, so I can tell you later about this. Yeah, because I did that, but it's also very different because in ADS3 you don't use any of these transformations, and you have momentum space on the nose, so it's a bit different. But indeed, something that I would love to understand, for instance, this is the kind of questions why I wanted to tell you what I wanted to talk about today, is that I would like to see whether either from string field theory or from pure spinors, you can see some of the structure that I am going to describe.
Do you have any geometrical intuition about what S and T is? Usual scattering amplitudes are just square of momentum, right?
That's right, that's right. So, right, so that is also a beautiful question. So here I only know in the flat space limit. So in the flat space limit, they are the same thing, but indeed for something like ADS, you cannot define momentum. So here, although I am calling them in the same way, I should have given them a different name. I should have called them with some different notation, because they may be not related to the Mandelstam variables. However, I know that in the flat space limit, this is precisely the Virasoro-Shapiro amplitude, where S and T are precisely the Mandelstam variables. Yeah?
Can you ask about this flat space limit? Let's say at the number 2 level, is this now proven? Because in the original...
No, the only thing that is...
was always phrased as conjecture.
The only thing that is proven, right, it's always... not proven in the sense that it works case by case. I don't think it is proven. Also, non-perturbatively is a bit hard to see. Ours, I think, is the first paper where we check this for the full Virasoro-Shapiro amplitude, while all other checks were for diagrams. So you would do a quartic diagram or an exchange diagram in ADS and see that under this, it goes to the flat space limit.
But I mean, is it actually hard to prove? I mean, I would have to imagine, at least for quantum field theory ADS, if you use like Hard-Rel and kind of scattering theory approach, I would imagine.
Yeah, I think that's that's the way. Well, okay. So there is what they call a proof, but I don't remember precisely their assumptions. Yeah. So in a paper by Penedones, they put, and then there is another paper by Kaplan where they start with wave packages, and then they land to exactly this. But all this is for the R equals infinity limit, in that limit. Yeah. Good. Okay. So yeah. So let me go a little. Let me push forward. On the other hand, one can do also the same for open strings, and for open strings, let me copy this here. The structure is very much the same. But now, at order k, in S&T, you get something like the Veneziano amplitude, and at zeroth order, you would get only this. But if you are computing at the kth order, you get an additional insertion, and this additional insertion is something which is a polynomial in S&T and is a harmonic polylog in X of weight or degree 3k. So, as I mentioned before, is there any questions? So the structure, notice that the structure is very similar to the structure for closed strings, but the difference is that now an integral, instead of being an integral, over the complex plane, is an integral between 0 and 1. These harmonic polylogs usually have branch points at 0 and 1, and branch cuts to minus infinity and from 1 to plus infinity. However, because we are only integrating them between 0 and 1, they are well defined, and they are canonically defined, and that is the answer that we have.
These are massive string states?
Yes.
And momentum on S5 is 0?
That's correct. Yes, that's correct. Yes, that's how, yeah.
Okay.
Yeah, good. So what I wanted to tell you now is some patterns. So basically what we have done in our papers is that for both closed and open string amplitudes, we have found the answer for k equals 0, 1, and 2. So for the first two curvature corrections. And the way we have done that has been by matching the poles of these expressions to the spectrum of n equals 4 or the corresponding n equals 2 theories. But something that we would like to do now, two things, is one is to look for patterns of our answers, and the second thing is to try to understand whether this worksheet picture teaches us something. And the kind of very interesting questions that we would have is kind of questions like what Nathan was saying, whether this set and this x would be the same as the sets and x's of a true string theory computation. And this is the kind of things that we want to understand. Now, in order to do that, in the next like 10 minutes, I have to explain you a little bit about these harmonic polylogarithms, okay? And that's what I am going to do now. Any questions before I proceed?
Can you remind me, did you have any positivity in your input?
No. And the reason why you don't have positivity is because in an expansion, when you have an expansion, you have that the first OPE coefficient, let's say, is positive, but all the others are corrections to that OPE coefficient, and corrections can have any sign, really. So positivity doesn't play a role in what we do. Yeah.
Can you maybe explain is there some quick explanation of why is it possible to infer precise information about the massive poles from the Lagrange expansion? And I think that would have thought that without some kind of positivity or some rules like...
Oh, sorry. We do have dispersive sum rules.
Okay.
Sorry, I apologize. So, yeah, sorry, I take it back. So we do have some dispersive sum rules. When you use dispersive sum rules in a non-perturbative in 1 over lambda, you do have positivity. And then using these sum rules, we derive relations between the Wilson coefficients and the CFT data of our theory. Sorry, I take it back. I misunderstood your question. Yeah. So we use some rules and dispersive sum rules, indeed. Beautiful. So this is the structure of closed strings. Here we have some single-valued multiple polylogarithms. For the open string, we have the usual harmonic polylogarithms. They are multivalued, but we integrate them between 0 and 1, so we can always do that. So let me give you some examples of harmonic polylogarithms. Usually, they are described by a word which is a string of zeros and ones. So you have, for instance, the empty word, the word 0, the word 1, the word 0 and 1, 0, 0, 1, etc. So your alphabet are the letters 0 and 1, and with that you do a word, okay? And the L's are labeled by one of these words, right? And they are functions of x, such that L of the empty word is simply 1, L0 of x is log x, and L1 of x is log 1 minus x. So for instance, you can see here that this will have a branch point at 0, and this will have a branch point at x equals 1. And then for higher, for words with more than one letter, we define them recursively as follows. And the definition is that if you have L of omega and a letter A, and you take the derivative of that with respect to x, you get 1 over x minus A. Here A is either 0 or 1 times L omega of x. Okay? And such that L, when you have 0p times, this is L p to the x over p factorial. And if you have L for any other letter, any other word, sorry, which is different from 0 to the p, and you do the limit as x goes to 0, this is 0. So basically, if you take this differential equation and you supplement it with this boundary condition, then you uniquely find this, okay? In practice, notice that if you have at weight 1, you will have log x and log 1 minus x. At weight 2, you would have the square of these and the logarithms at weight 3, 3 logarithms, and the cube of all these things, and so on. Is that okay? Any questions?
Sorry, the weight is the length of the word?
Yeah, sorry. And the weight. Indeed, is the length. Yes.
If I could just, the single value logarithm.
Yes.
They are really well defined on the sphere, not only on the plane. So you can check that.
Yeah, that's right.
And do you have something analogous to the like crossing for the open string too?
That's what I will discuss.
Ah.
Yes, yes. That's the closest thing are the monodromy relations, which I will tell you about. Yes. Yes. Good question. Thank you. Any other question? Very nice. So I think I wanted to discuss. Okay, maybe very quickly let me mention one pattern, which is quite nice, and then I will go to the main pattern in the last 10-15 minutes. So let me take 5 minutes to mention something. So something that we can try to understand with these answers is whether there is a regime of S and T where we can compute the answer to all orders. Okay, and indeed there is one such a regime, and this regime is the high energy limit and this is a limit of large S and T with S over T fixed. And this limit has been described by Gross and Mende like centuries ago. And the nice thing is that if you have an integral representation, let's say for the closed string amplitude like this, or for the open string amplitude like this, you can compute the answer in the large ST limit by saddle point, by a saddle point approximation, okay? And in the saddle point, we find something like Z is equal to Z bar, which is equal to S over S plus T. This is the saddle point. Sorry?
For all K?
This is right. So this is in flat space. This is what Gross and Mende did, right? Indeed. But indeed what happens, so Gross and Mende, they did it for K equals 0. But you see that because in our proposal, the dependence on S and T is a polynomial dependence, right? Then the saddle, the location of the saddle, will be the same for all K. Okay? So that actually the saddle point in a 1 over R expansion we get the same saddle. And here I want to stress that this is true only in a 1 over R expansion. So the limit we are taking is the largest thing is 1 over R, and then for every order in 1 over R, we look at the high energy limit, okay? And then you can see that the location of the saddle is the same because the dependence on S and T is a polynomial dependence here, okay? And then we find something quite cool and quite surprising. So here, notice that this, for instance, this omega 3 for K equals 1 is some linear combination of these functions for weight 3. There is basically 8 of them. Now when you go to weight 6, there are many, many of them. There is something like 64 of them, okay? And what we found is that at this saddle point, let's call it Z0, W6 of ST and Z naught is actually precisely the square are subleading in the regime we are considering.
Sorry, when you say the next term, I mean, I thought this term is already suppressed by power alpha prime, no?
That's right. And you can compute further corrections to that.
But I'm saying, like, this term, I wouldn't expect to get it from the classical action because that's like,
You can compute, right. So you can compute this term, sorry. So there is a term that you can compute that is from a classical action on ADS.
which term is it?
And this is the term we compute. I have to see, I don't remember if there is an alpha prime here or not. But this is a classical. This you can recover by a classical solution. And in the classical solution, you can show that it exponentiates. And this is the, yeah, I have to see the paper to check whether.
When you say classical solution, do you just mean Nambu-Goto in ADS?
Yes.
I see.
Yes. So if you consider a Nambu-Goto, we consider the Polyakov action. If you consider like a Polyakov action in ADS, and you find classical solutions, you find exactly this structure as well. Yeah. So no alpha prime, sorry.
So just to understand, the limit you are considering is alpha prime is very large, but
Right. So
Dominates over the leading term.
that's right. So I am considering a limit in which this is very small.
Exactly.
Yeah. Or, in other words, I first do this expansion, and then to each order, I consider the high energy limit of each independent order. And my claim is that all these leading terms, they exponentiate into that formula. Okay? I will go back to that formula in a little bit. It's not what I wanted to discuss, but it's just to tell you that there are some limits, like this limit here, where we can compute something to all orders. Okay? Okay, so something that I did want to discuss, and can I take like 10 minutes? Is that okay? Yeah?
What is the precise definition of S and T?
Well, the precise definition is in the chain of transformations that I wrote before. So you have a correlator, which is a function of U and B. From that, you go to the Mellin amplitude, and from that, you go to the Borel transform.
But
And
you don't know a priori the conformal dimension of these operators because they are very far from BPS, right?
the external operators, they are BPS operators in N equals 4.
You told me that momentum on a sphere is 0.
I told you that too, but it's, sorry. So it is like 2, so that it doesn't scale with R, so it stays small. So the operators are operators in the 20 prime.
So
They are small, they don't scale with R.
sorry, I don't understand. They are not constant on S5.
Yeah, they have R charge that is like 2.
So this is BPS.
They are BPS states, yes.
Okay, now it's better. Thank you.
Yeah, they are BPS. I would love to do non-BPS, but they are BPS. And when you take this flat space limit, they match to massless scattering in flat space. Good.
I mean, if you were BPS, you also really want to go into expansion. That makes sense.
Right. Okay, so let me now very briefly discuss something that we are quite excited about, and we would like to see if some worksheet direct computation has the same kind of ingredients, which are these monodromy relations. So, as in the question of today, we know that for closed strings, the amplitude is fully symmetric under exchange of ST and U. On the other hand, for the open string, that is not true, but for the 0th order in flat space, we have what people call the monodromy relations. So the monodromy relations are some relations as follows. And this is equal to 0. So these three are color order amplitudes, and they are not independent, but they have these two relations over here. And these monodromy relations, they have a very nice worksheet interpretation, and you can actually prove them with some contour deformation. So this is in flat space. And basically, I guess something that you could write down is that if you consider a disk amplitude, where you put operators, one operator at 0, another at 1, and another at infinity, and then you get the 4th operator, and you make it travel all around this integral over all this is actually equal to 0. And the integration from 0 to 1 gives you the first term. The integration from 1 to infinity gives you this one. And the integration from minus infinity to 0 gives you this one. And these prefactors are what happens when this operator crosses one of these operators, the operator at 0 or the operator at 1. And here you have two choices. You can cross them this way or the other way, and these are basically the two signs here. Okay? Now, what we would like to do is we would like to understand whether this extends to ADS as well. And notice that in ADS, the structure of the answer is the following. Let me write it again. Actually, let me erase here. This is the structure of the answer. So there is this factor, for instance, and what happens is that as x goes around 0, we pick a monodromy factor. And basically, e to the plus minus I pi s is half of that factor. And this corresponds to the picture I just erased of crossing the operator from above or below. Is that okay? Beautiful. On the other hand, for ADS, we now have these two, right? And what happens is that although this integral is defined between 0 and 1, if you try to go around 0, this will also pick a factor, okay? And this factor is actually controlled by the monodromy of these polylogs. And there is an operator that we can introduce. We call it K0. And by definition, this operator K0 is such that if you act with K0 on a harmonic polylog ending in the letter 0, you get the harmonic polylog without that letter. And if you act with K0 on a harmonic polylog ending on the letter 1, you simply get 0. And actually, what one can show is that the monodromy around 0, this was shown by Francis Brown, x is equal to 0, is given by the monodromy operator, which is e to the 2 pi I k0. So if you have e to the 2 pi I k0 and you act on these polylogs, the simplest is just on some bunch of logarithms, you will see that you produce the monodromy around 0. Yes, sorry.
Well, the open string is computing what? It's correlation functions of...
Yes, sorry. So this, I explained this a little bit on Friday, but not today. I apologize. So, so it's an n equals 2 theory. What you can do is you can start with ADS 5 crosses 5, and you can put some brains. And basically, it's the scattering of open strings in that brain.
Just tell me what the symmetry is. What is supposed to be the symmetries? It's not PS624, it's some subgroup.
That's correct. So it's on n equals 2 theory with is SU2 cross SU2 cross U1. And yeah, it has some flavor symmetry that we don't need to specify. Thank you. Beautiful. Then we have this monodromy, and basically this operator K0, sorry, can I take like 3 more minutes? I just want to write down these monodromies. So this operator K0 may look very weird, but if I give you, for instance, L01, and you act with K0, you kill this, while if you act on L00, you just produce L0, okay? And this is just computing the monodromy around 0 for logarithms, which you know they pick this, you pick a 2 pi I discontinuity. In the same way, you can compute the monodromy around 1. The operator is a bit more complicated, but basically is called e to the 2 pi I k1. Now what we have found is that one can correct the monodromy relations in flat space, and the precise monodromy relations in ADS are the following. Here you have S, and you enhance to S plus K0, acting on K, SU, plus I pi T plus K1, acting on K ut. And now let me make 4 very brief comments, and then I will ask questions. I will take questions, sorry. So basically the idea is that if you have you have the amplitude written as this, the operator K0 and K1 will act on these L's inside here in a very prescribed way, and once you adapt these 3 terms, you get exactly 0. Okay? Now the first thing is that this, although it may seem a bit trivial, it is actually highly non-trivial. And for instance, to see how non-trivial this is, for k equals 1, for the first correction, the general ansatz has 33 parameters, and this monodromy relation imposes 28 constraints. So out of the 33 solutions that you could have been write down at weight 3 for the first correction, only 5 of them survive if you apply these monodromy relations. We, in addition, check that for k equals 1 and k equals 2 works. And to me, it also, okay, there is also some comments on the high energy limit, but to me, the most beautiful comment is that we need the worldsheet. So this relation is a relation which we could not have guessed unless we have a worldsheet representation for these integrals. Because notice that the way these operators K0 and K1 act, they don't act exactly on functions of S and T, but they act on the integrand of this by computing these monodromies around 0 and around 1. So for instance, this relation, going back to your question, tells you that whatever variable x that you use for your worldsheet in open strings, it will have to satisfy this relation here, and our variable x satisfies precisely that relation too. So only with this definition of the worldsheet variable, we get such a neat monodromy relation. Anyway, thank you very much, and then I can take questions.
In flat space, you're talking about 10 dimensionals just ordinary open strings?
Yeah, I mean, you don't even need to specify that you're in 10 dimensions. But if you're in, yeah, you are in 10 dimensions, but of course,
I need full supersymmetry.
sure. So you're in 10 dimensions, but the momenta of the gravitons could be on a plane. Yeah.
They're not gravitons, it's gluons, right?
Sorry, gluons, of gluons, yes.
So, but it sounds like you made many choices when you did the ADS. What is
Space limit is some theory on a D7 brane, but we did it for many different theories. So you can do a scattering of open strings in many ways, but because we are only considering 3-level amplitudes, all these ways are very similar.
I see. So there's no extra parameters. You just have a unique answer.
There is one extra parameter which has to do with the flavor symmetry. So indeed, at second order, we get one free parameter, and that one free parameter has to do with the flavor symmetry, which is a discrete choice. Yeah.
So just to understand the precise 7-brane setup, do you have oriented pose?
Yes, you can have oriented pose, yes.
I mean, usually I would think that you have to have oriented pose, otherwise perturбation theory is not well defined. I mean, like in the 7-brane background.
Yeah.
Like if you go to, again, perturbatively might be okay, but not perturbatively.
Yeah, absolutely. So you're correct. So non-perturbatively, you have to have. Perturbatively, you can do many things. Like, for instance, this when you add flavors to a DSCFT, you are in some quench approximation where you add a few D7 branes. Because this is a 3-level computation, all this. So I think we could have problems doing a one-loop computation for the open string. Yeah. So in that sense, the closest string is on a much firmer footing. Well, for open strings, you are correct. So this is perturbative, and non-perturbatively, you will have to have oriented pose, yes. But they don't play a role yet.
Let me see if I understand this monodromy relation properly. So your harmonic polylogs were sums of various terms.
Yes.
With coefficients which are functions of SLT.
Which are polynomials.
Which are polynomials.
Yes.
And somehow when you compute the monodromies, those reassemble and you don't get any SLT dependence except for the amplitude.
Yes, absolutely.
Exponentiate k and nothing else happens.
That's right. So like basically here, yes, so you will have some polynomials. Let's say at degree 3, you have some polynomial of S and T multiplying L000 of x, some other polynomial of S and T multiplying L101, etc. A list of all 8 of them. Indeed, and the claim is that when you act with this operator k, as I described, and you multiply by this, as I described, and you take all this and put it here, and you sum it up, you get 0. But you will get 0 only for very special choice of these polynomials, which before we missed. We didn't know that these polynomials. Because in a way, in order to get these relations, you first need to think about a worksheet, and then you need to get a little bit away from the 0 to 1, from that segment. Yeah, thank you for the question. Yes, oh, so, I think.
A follow-up is, can you do you have then an expression for a KLT matrix? Or implement a single value projection?
Yeah, that's a fantastic question, actually. We have been trying so much. So we do have some kind of KLT relations only for the building blocks. So I know how to relate integrals of these with harmonic polylogs to these sort of integrals with single-valued polylogs. That we know precisely how to relate, very much a la KLT. However, an amplitude is the sum of many terms, and for the amplitude, we haven't yet found nice relations where a precise closed string amplitude is equal to the square or the single-valued projection. We have tried.
Right, but just the building block, you know how to write as maybe a sum of squares.
That we can do. That we can do. Yes. However, the sum of squares we cannot recognize yet as amplitudes, open string amplitudes in ADS. It's just some sum of squares of these integrals, but we don't know what to do with that yet.
If you didn't start with such a simple action of K0 and K1 on these words, and you just allow it to be some arbitrary operator that closes within the space of these single-valued multiple polylogs, then would it still be highly constraining that you can write?
Beautiful question, because that's how we found them. Like, because we didn't know. But because actually K0 is very simple, K1 is much more complicated, and it has this Stringfeld associator on it. Because these harmonic polylogs, their symmetry x to 1 over x is not so simple. It's not as simple as exchanging letters 0 by 1. It has this Stringfeld associator. So indeed, we put kind of an operator here and another operator here, and we can kind of try to find them case by case. And then we found, but this is nothing but the monodromy. So I think in the paper we will present it as this has to be true, and then we check it is true. In reality, we spent several weeks trying to find some relations. And when I say we, I mean Rodrigo and Aurélie, my two students, and they found this beautiful relation. And then we interpreted them as, well, our student. We interpreted them as this, and we saw that it has a beautiful worksheet interpretation. But we found them exactly as you were suggesting.
I had a comment, but I don't know if you considered this. I mean, if you just tried to deform flat space into ADS by just adding the Ramon block and maybe a graviton.
Yeah, that's what we, yes, that's very good point actually. And that's kind of how we, indeed, that's how, so we did start, you can also consider a 5-point amplitude with an extra graviton, soft graviton, and then integrate over the location of the graviton. And if you do that, you can prove that you get a single valued polylogarithm of weight 3.
Okay, but you land on exactly what you want?
We don't land exactly on what we want because we have only done a toy model.
You need the two Ramon.
That's correct. You need the two Ramon, and you need the full computation, which has many terms. The phi graviton amplitude has hundreds of terms with some polarization dependence. We just did a toy model. But if you do a toy model, then...
You don't want the full one. You just want to choose the graviton to be in the ADS direction. So you fix the graviton.
You could fix some things, yes. So we did a toy model, which goes along the direction of what you are suggesting, because what you are suggesting is like doing the computation.
But I don't know if I'm computing this. That's what I'm asking. So is that the computation that computes this?
I would have to think.
I think it's going to be quite literally that, because the graviton is slightly off shell.
Right.
At first order, you have the Ramon, which is first order on shell, and the second order, you have the Ramon, two Ramon, and the graviton. And there's an anomaly from the two Ramon colliding that, right?
Yeah.
So it cancels. So you need both.
Yeah.
You have to correct it, but the question is that a string computation? Is there a string computation you could do in principle, which would compute?
But that's essentially what string field theory was.
That's a string field theory. That's the string field theory
The correct
computation.
way to do this is string field theory. I
Yeah.
mean, sometimes you can cheat a little bit by
Yeah.
not using the full string field theory
Yeah.
machinery, but there will be ambiguities.
So if that's correct, then he doesn't have to go through all this Melman transform.
In principle, that would be
If
beautiful.
that's the definition of this, then I'm happy. Then you don't have to say anything about Melman transform.
It's not clear how he defines asymptotic state.
Yeah, that's what I'm asking him. So if it's defined in flat space, then I'm happy. But that's not how he's defining it. So it's not obvious to me.
It would be beautiful to obtain this from a string field theory or pure spinor. Yeah.
I'm not asking if I can do it. I'm just saying, is that the definition of it? Or is it, I mean, suppose you get a different answer. Does that mean you're wrong, or does that mean the computation is wrong, or does it just mean that
You will have to agree also change your basis. But
Yeah.
It's not, of course, it's not obvious from that point of view what basis you start with. Because you might imagine you just start with the plane wave basis and then you add the corrections, but I don't know if you actually literate that on
No,
this.
I'm not
Maybe.
doing plane wave base. I'm doing flat. So I'm just expanding.
No, but that's what I'm saying. Like you have to decide like you start with a flat space 4-point amplitude, like you have plane wave basis for asymptotic states, and then you add corrections. But there might be some subtle, change of.
That's what I'm asking him.
Yeah. And there could be, for instance, some corrections to what I call S and T. So S and T could have 1 over R corrections, and I am using something, and that's why I would love to see some of your answers so that I could look at both things and compare. Right? Yeah.
But ultimately, it shouldn't matter too much because the amplitude is basis independent. I mean, okay. I mean, of course, the formula will change if you change the basis a little bit. But
That's
but
correct.
there's,
Absolutely.
there's
Yeah.
data that is independent of it.
That's right. Yeah.
He has this SVMPL, right? Is that the same? Does that follow from the flat space expansion, or is it something that?
At the end of the day, all will have to be encoded into the 4-point function of n equals 4 superanimals.
No, I understand that there's an answer you want to get, which is the one that you get from the Mellon transform.
Yeah.
The question is if that's the same answer you get from the string field theory computation.
I think up to a change of basis. I would be extremely surprised if it is the same on the nose.
SVMPL thing follows from the string field theory.
No, I mean
The structure will
it's
be
not
the same.
obvious you land on the exactly same basis, but you know, a priori because you know you can start doing your perturbation theory around some plane wave basis, but you know ultimately you need to study the linearized fluctuation around the ADS solution. You know.
But is the SVMPL basis dependent or not? Because that seems to be crucial for you.
This actually, notice that if you want to integrate something on the worksheet, whatever you have to integrate has to be single valued on the complex plane. So here you cannot put anything you want. So it will have to be something single valued. Otherwise, even the integral doesn't make any sense.
Okay.
So the kind of questions.
So you think it's basis independent?
This statement, yes, but the precise answer, I would expect so. I would expect so. But because I am so ignorant about string field theory, I don't know. Yeah, it would be nice to see. And again, there is data, like the dimension of Konishi should arise from both computations in some way, and that is kind of data independent.
Yeah, I mean, the most naive thing you would, I would do at order 1 over square is literally just to stick into our vertex operator, add the PCO. Yeah. Now, presumably, if you do that calculation, you run into some ambiguity, and then you can try to correct for that. Right? I mean, that's kind of the shortcut you would try to take. And sometimes you can get away with it, sometimes not.
Yeah, I agree, but it sounds like there's an answer you want to land on, so that's why it'd be nice if you land on it.
Thank you.
Okay, so
Thank you.
5-minute break.
Thank you. Thank you, Pedro.
Yeah, I still want to understand better the open case. I don't have much intuition about what are the choices. So the symmetry algebra is what? So it's
It depends a little bit on the theory, but you have n equals 2.
so you have 16 supersymmetries.
Yeah, n equals 2 in 4 dimensions for the simplest case.
Ah, so you don't even have any conformal.
No, it's n equals 2.
But superconformal?
Yes.
Okay.
It's n equals 2, and the symmetry group is SU2 left cross SU2 right cross U1. We are super specific on the paper. It's just that.
No, I understand.
And one can define. Let me use the restroom.
Yeah.
And then.
The equation would be 4 fundamental hypermultiplets and 1 antisymmetric hypermultiplet.
Say it again.
So n equals 2 superimperials plus 4 fundamental hypermultiplets and 1 antisymmetric.
So it's advertising.
Advertisement. How do you deal with that?
I have a seat for overweight. Okay, so remember that tomorrow it will be at IFT. So if you've never gone, I will leave at least 40 minutes to get there. So it takes 30 minutes if you don't get lost. You have to get a ticket, or I think you can pay by credit card.
Yeah, I think so. To go there you can, but then to come back I'm not sure if it works. So maybe
But
it's better to buy.
Uber would work?
Yeah, Uber.
You know where the metro station is, right? Everybody knows where it is, Chinon Mas? It's just at the end of Pamplona. So you just have to buy, there's a booth, you just buy 2 tickets to go and come back. It's a little sheet of paper that looks like it's a coupon or something. And then you can go as long as you, I mean, there's no, it's not like, you don't pay by region. So if you get off at the wrong station, just get back on. You don't have to get another. Okay, so
All right. I'm gonna make some comments about the matrix string theory. This is mostly going to be kind of a review slash kind of reinterpretation of all results, but it's also based on some ongoing work with Minjae Cho, Braga Bai, and my student Jaroslav Scheinflug. So far has some modest results, but you know, we would like to have more, so we don't know when we'll publish anything. But anyway, so the subject is almost 20 years old, but I think it's one of these things that was ahead of its time. So I'd like to kind of discuss what matrix string theory is from kind of perhaps a more modern perspective, and you know, why I think it's important. So just to, I would say like it's the reason I'm interested in this is at least for 3 different reasons. First of all, I think as I'll explain, it gives us so far the strongest evidence for what is known as sort of the strong version of the BFSS proposal, which I'll discuss. It's also what I think is the correct way to do light cone string perturbation theory. That's the point number 2. And point number 3 is that it can potentially, to my best knowledge, it can potentially give a non-perturbative formulation of the type 2A S matrix in flat spacetime. But let me first just explain what the duality in question is. The duality that we're going to actually, I had a better. I had a good one, but then I lost it. Okay. This one is good. Okay, so the duality, which I'm going to motivate in just a moment, is a relation between type 2A S matrix in Tandy-Minkowskian spacetime, and a particular observable of the 2D maximally supersymmetric, let's say SUN, super-Yang-Mills on a circle in a specific, let's say specific angle to infinite limit. I will discuss exactly what is the observer we're talking about. And the upshot is that what we believe, or at least I believe, that you might be able to get the full non-perturbative S matrix of arbitrary string states from this object at the bottom, which is a purely field theoretic quantity, even though it's not necessarily under practical computational control at the moment, but at least we think it's in principle well defined. But first, let me motivate this from a holographic duality, and I also want to say that I also want to say that one of the reasons I say that the matrix string theory was ahead of its time was that it goes beyond the standard ADS safety paradigm. And I'll hopefully make that clear. But let me first discuss sort of the ADS safety version of it, which is not the thing that I'll ultimately be interested in, but it's a thing that is more kind of on a firmer footing that we think we all would agree on. That is, we begin with type 2b in asymptotic flat space time, and we'll consider ND1 branes. And we all know that there's the extremal one brane solution. That's no, but let me just write it down just to make us all comfortable. The string frame metric is from some warp factor minus dt squared plus dx squared plus f to the plus 1/2 dr squared plus r squared d omega 6 squared, 7 squared. And there's where the function f of r is some number times n over r to the 6th. There's a dilaton e to the phi goes like f to the 1/2, and then there's a Raman 2 form goes like f inverse dt dx. Okay, so this we all know, and of course we all believe that this is dual to by the usual. I've taken the decoupling limit. So I've already taken the decoupling limit now, so that I throw away the plus 1 in the warp factor, and we all believe that this is dual to the 2D 8,8 super YAMLs with the UNO SU engaged group. Now, there are two things I'm going to do to this space-time background. We're going to first perform S-duality, the standard S-duality. So we're still in type 2b, but now we have a solution that is the string frame metric. This is a simple exercise. You'll find that it goes like f inverse minus dt squared plus dx squared plus dr squared plus r squared d omega 7 squared. E to the phi, of course, gets inverted, becomes f to the minus 1/2, and the C2 turns into B2. So this is an NS background. Right? Now, I'm going to now compactify x on a circle. Now we're allowed to do that, and here, the deal n equals 4, not n equals 4, deal to 8,8 super YAMLs is now also going to be compactified on some circle, some radius r. So I'm going to compactify. Of course, I just identify periodic identify coordinate x, and then I'm going to perform T-duality, which I can also do. And if you just use the Boucher rule, this is all elementary. This is a surprise. So the dual, the T-dual metric is 2 dt dx tilde plus f dx tilde squared plus dr squared plus r squared d omega 7 squared. You will find that dilaton is constant, and there's no flux of any kind. So I don't even have to say the string frame. No. So this is just pure geometry. And if you chase down the relation between these two, you'll find that so now, of course, we're now in type 2a string theory. So this is let me say that x tilde is like x tilde is identified with tilde plus, I guess, 2 pi alpha prime over r, as usual. So in the TDO description, so we're not in type 2a, in the pure geometry background, no flux of any kind, constant dilaton. So there's a well-defined type 2a string coupling, GA, and if you chase down the dictionary, you will find that this is equal to identify with, on the 2D gauge theory side, 1 over G Young Mills times radius. There's some number, like square root of 2 pi. I'm not worried about that on the board. Okay, so that's the relation so far. So the conclusion so far is that there's this holographic duality between type 2A string theory in this background and the 2D maximal supersymmetric Young-Mills theory on a circle of radius r, and the Young-Mills coupling is related to the string coupling by this inversion. Okay, so that's that. So this is the standard holographic version of duality. There's nothing controversial, hopefully. Okay. Let's see. There's one. Okay. So now this is sort of you see this compatification is asymptotically null. So this is just like BFSS background in M theory, except that it's reduced by 1 dimension. So the BFSS is just like the M theory on a similar thing, where this 7 is replaced by 8, and instead of this maximal super Young-Mills, you have the BFSS matrix quantum mechanics. Now you can say that this is just a generalization of that.
Sorry, dt squared, how did it become a dt dx tilde?
There's some term from the B2. When we apply the Busher rule, there's off-diagonal component of the metric that, yeah, if you just change down that, you'll find this. Right.
Those BFSS should be null direction, should be compactified, isn't it?
No. Okay. So the yes and no. Okay. So in the original BFSS proposal, that was a proposal. However, if you follow the standard logic ADS-CFT, what you would say is that you start. So I can replace everything with instead of D1, I talk about D0. I can chase down the same thing, and I uplift instead of doing the duality, I just uplift M theory. You end up with something very similar, just like this. Okay, and you'll find this term like this. So this background is non-singular. This is a it's only become singular at infinity. Right, so it's asymptotically null-compatified, but any finite distance is not null-compatified. And that, I would say, is the holographic dual of the D0 quantum mechanics in the holographic sense, in sense holographic duality. Now, the BFSS, the original proposal, took that one step further. They want to say something about the flat space S matrix. I'll come back to that. But at least in the holographic interpretation, this will be the actual background. So it's non-singular. It is not null except at infinity. Yes, it is. That's what it is. I should also mention this curious fact that now you might say that, okay, this pure geometry background, you can just quantize string in this background. I don't actually know how to do that, just because it's intrinsically Lorentzian and it's a bit singular. And the standard toolkit of the worldsheets conformal field theory based on nonlinear string model, it just, I don't know how to properly think about the quantum worldsheet theory in this background, but of course, we think this is benign. The singularity is not an issue, but in practice, it seems to go a little bit outside of our standard toolkit if you want to use the kind of the worldsheet CFT formalism. Okay, in any case, so this is the holographic version of the duality.
Classically integrable?
Classically integrable. That I don't know. I guess that's the kind of question I would direct to you instead. So
one should redo the thing of Bena, Polchinski, and Reumann, but for this sigma model.
Yeah, yes.
No, but it's
You don't have symmetries, so you don't have group elements and so on, but you would make an ansatz implied connection and try to find it.
But it's not an exact solution to alpha prime order. It's a wave, but it's not
I think whether
it's not a conformal sigma model, an exact conformal sigma model.
first of all, I think whether you call it exact or not is scheme dependent. It's scheme dependent. I think, but on the other hand, there is problem. So that's the thing I was alluding to. I don't know how to precisely define the worldsheet theory as a quantum CFT. For example, I cannot do conformal perturbation theory. I cannot treat this as a perturbation, right? That makes.
Backgrounds that are exact sigma model
I'm saying that for this one, I don't know how to define that. One reason is just because I cannot treat this as a perturbation. So, because if I delete the term, the whole thing makes no sense. The whole thing is singular. So this kind of crucial, and I don't have a very useful way of doing perturbation theory in alpha prime, let's say. Anyway, but I think we can all agree that this spacetime is supposed to make sense. And okay, so this is the sort of the hologram version. You can do various things about this, but that's not going to be the thing of main interest to me. The thing that's going to be of interest is to consider a further limit where we're going to claim that there's a limit on certain observer can take that lands you at the flat space S matrix. The idea is basically that okay, so maybe to motivate that, let me first say a few words about the Hilbert space and some kind of some notion of S matrix in the super-Yang-Mills theory on the circle. You know, it's just working very naively, you might think that you know, because the GA is identified with 1 over G Yang-Mills or 1 over R, sort of the low energy expansion is related to the perturbed string expansion, and that's going to be correct. So let's discuss a bit of what is the low energy dynamics of this 2D, let's say UN super Yang-Mills. Yeah. Sort of the kind of the standard claim, which you can justify by various ways, like non-realization theorem on the low energy effective theory around the modular space of vacua. The infrared limit is the symmetric product of n copies of R8. By that, what I mean is, by this R8, I mean the supersymmetric sigma model with the 8 bosons, 8 fermions. But more precisely, I can say that it's I have let's say the 8 bosons where this lower index A labels 1 to n, and you think of this as the eigenvalues of the 8 scalar fields in the super Yang-Mills, 2D super Yang-Mills that are mutually commuting. So you're kind of expanding around the vacuum, the classical vacuum configuration. And then you've got some theta A alpha and the theta A tilde, let's say alpha dot, where this alpha and alpha dot are the SOA's chiral and anti-chiral spinor indices that inherited from the fermions of, let's say, the gauginos of the super Yang-Mills. But also restricted to this kind of vacuum configuration. So you basically take this set of the theory with these boson free fermion fields and model by SN. Okay, so that's the symmetric product theory.
Sorry, can you say a few more? Can you do it a bit slower? So are you saying this arrow going down is trivial, or it was the result of many papers? Or?
Well, this is I actually don't know who first made this claim. It probably goes back to Seiberg, you know, something like that. But it's based on the standard logic. You know, it's just that it's based on the idea. Okay, so at least one way I can think about this, which I think is maybe the kind of the most conceptually straightforward way, is to say that you start with the classical vacuum configuration, which are parameterized by you know, these mutually commuting scalar fields. These are matrices and they mutually commute, so you minimize the classical potential. You have these massless fields, and then you can ask, you know, what are the possible quantum corrections? But the standard supersymmetry non-realization theorem will tell you that the corrections will occur at, you know, 4 derivative to order and higher. They are not relevant in the infrared limit, and you just end up with this free theory, except they have to order followed by this Weyl group. So this is the usual logic, and we believe this is the correct conclusion. In fact, the early papers on matrix string theory often refer to this symmetric product, and I think this gives people kind of the false impression that the matrix string theory is about the symmetric product. I want to emphasize that that is not the case. Okay, so this is a very boring theory. We know everything about this theory. There's nothing terribly interesting. Of course, you can say that, okay, if you look at the Hilbert space of states, you can find, like, you can interpret this as multi-string states, fine. But that's a free string theory. So this thing, in some sense, you can say that it's dual to like free strings in flat space if you wish. That's not of interest here. We're going to be interested in the dynamics. The point is not to be working at infrared fixed points. Well, as you see, indeed, if you just follow the dictionary, you take R to infinity, the G equal to 0. So that's the free string theory. We're going to be interested in at least turning on a little bit of the string coupling. So we go away from the infrared fixed point. So going away from the infrared fixed point, from the point of view of conformal perturbation theory around the IR fixed point, you can organize your corrections in terms of let's say adding to the action irrelevant operators. And the first correction is going to be sort of the leading irrelevant operator that will be compatible with the symmetries of the problem. It will turn out to be the following. Moving away from infrared fixed point, the first correction to the action is going to be the integral of a dimension 3 operator called sigma of x with some coefficient, there's some number, and over G on mils. This factor 1 over G on mils can pin down by dimension analysis, but you have to, this number, let me emphasize here that this, okay, so this is, I'm going to return to this number in just a moment. It's not pure number, okay? The sigma is what's known as the digraph Verlinde twist field. Let me tell you about the property of this operator. So this is a primary, conformal primary of weight 3/2, 3/2. It's dimension 3 operator. And it's in the twisted sector of the symmetric orbifold theory. So let me write something a bit more precise. So the sigma, I can write, okay, I guess unfortunately, okay, maybe I'll call it little sigma so that I don't confuse the sigma with the summation sign, which I'm about to make. Let me call this thing little sigma. So this little sigma is going to be a sum I less than j from 1 to n sigma ij. Let me put a parenthesis here just to so that this ij represents a permutation. Okay, so this is in the twisted sector. So in the twisted sector operator. And what this thing is that, we're talking about permutation orbifold. So if you're in a kind of a length 2 twisted sector, you can identify the space of states in that twisted sector with the space of states of a single copy of the theory, of this theory, on the circle twice as large. All right, so kind of describing this language. So in that language, I will say the following. So here, this notation is the following. So when I write this bracket, I mean that if you live to the covering, then you can represent as a vertex operator in a single copy of the theory. Okay, so inside the bracket, I'll just write an operator of a single copy of this free boson, free fermion superconformal theory, and that operator is actually nothing but G tilde, where this G and G tilde are the holomorphic, anti-holomorphic supercurrents of weight 3/2. In fact, sorry. There's one more thing I wanted to say. I forgot to say. Let me state that now. Actually, yeah, I was getting ahead of myself a little bit. One of the you can analyze this theory, of course, using standard CFT technique. But there's something you have to get used to a little bit, because in the CFT, usually when we speak of free boson, free fermion, we're used to thinking about NS and R sector. In this context, If you're talking about the actual states of the super Young Mills, you're always in the R sector because you're always working with the, by assumption, we have the supersymmetric boundary condition on the circle. So we're always in the RR sector. If you're talking about states. If you're talking about operators, then that's a different story. We'll come back to that. But if you're talking about the states, we're always in the R sector. So if you consider the Hilbert space of a single copy of the theory, I'll denote that by H1, so it contains sort of the oscillator ground states. Ground states are of the form e to the, you can take e to the ikx, you can take a plane wave basis, right? And you tensor with, so you're always, as I said, you're always in the R sector in the usual CFT language. You can take a holomorphic spin field tensor with the antiholomorphic spin field, and there is no GSO projection. Right? And the spin field, in this case, because this theta is sort of the elementary fermion, so the spin field will carry SO8 representation that is the other two related by triality. So you got psi I, and something I can call S alpha dot, and here you have psi tilde J and S tilde alpha. Okay, so these are the holomorphic, anti-holomorphic spin fields of that system, and these together form the oscillator ground state. And then, of course, you can add on with oscillator. This is okay. So this G here I'm talking about is a singlet. So it's singlet. This is the psi I partial xi, after some normalization. There are many different G's, because this is a particular G, which is actually a Raman sector operator. You can also talk about the Encos A supersymmetry. Their corresponding currents are not this G. It's some other G. In fact, I won't bother writing this on the board, but you can show, you can verify that this thing can also be written as the level 1/2 descendant with back to the 8,8 supercurrents, and use that to show that this thing indeed preserve 8,8 supersymmetry, which of course has to be. Okay, so there's some little gymnastics you can do. And you can also check that this thing indeed has dimension 3/2, 3/2, and the way roughly it goes is that this thing has dimension 3/2, but because in the cover actually contributes dimension 3/4, and then there's another 3/4 coming from the twist ground states, and together give you 3/2. Okay. So anyway, so you can, it's not hard to check that this is the unique, or the sort of the lowest irrelevant operator that's compatible with the symmetry of the problem. So that has to be the case. But based on this argument alone, you would say that, okay, if you go a little bit away from inferior fixed point, you have maybe this correction, but you don't know what the number is.
Make sure the G and G theta don't carry R symmetry labels.
They're single. You mean SO8 R symmetry? Yeah, they're singlets. That's correct. Excuse me. Okay. Now, I think it remains an interesting challenge to field theory experts, in particular for folks who working on localization, to pin down this number from field theory. I don't know how to pin down from field theory. However, I will be able to pin down this from the duality, from the conjecture duality. So I'll be able to tell you what this number is to some factor of 2 than pi's. Okay. Okay. Now, of course, there will be many more irrelevant operators, but exactly what they are scheme dependent. So if you do conformal perturbation theory, when the sigma collide, of course, you're going to have high dimensional operators, divergences, and depending on how you cut off, you can maybe use some point splitting, you'll affect the higher dimension counter terms. All of that are in principle data you can determine by the UV completion, but in practice, it's very